In section 3.5, we're going to take a look at curve sketching. What I mean by curve sketching is we want to find out what the graph of a function looks like without having to plot a bunch of points. In order to do this, we are going to look at just a few key points. And the few key points that we're going to look at are going to be ones that are associated with the first and second derivatives of the function. Now, you may ask why we would want to do curve sketching by hand, especially given the fact that we know how to use calculators and computers in order to graph functions. So why not just graph a function using a computer or a calculator? Well, the first answer to that is that curve sketching gives insights into the connections between the function and its first and second derivatives. The second answer is that this allows us to sketch curves without knowing what the actual function looks like, which is a key component when doing data analysis. So not only are we going to gain insight into what the first and second derivatives are actually telling us, but it also allows us to sketch without knowing the actual function, which is really nice when you're trying to deal with predicting behavior of raw data. The book and I go into how to curve sketch. In order to curve sketch, we want to do this in a stepwise process. To produce an accurate sketch for a given function f, we consider the following steps. The first thing we want to do is find the domain of the function. We're going to assume the domain is all real numbers, and then if I can't plug in values into the function, I'll restrict it from there. Once we've considered the domain, we're going to find the critical values. Remember, these are the values where the first derivative does not exist or are equal to 0. That'll tell me where the curve could possibly change directions. Third, we find the points of inflection of our function. Points of inflection are where the second derivative is 0 or does not exist. And this tells us where the concavity would change or could change. Now, as you're finding the domain, you're going to want to think through where vertical asymptotes of our function could be. This is, again, in the same realm of finding the domain. We also want to find out the behavior of the function as x goes to infinity and as x goes to negative infinity. Do you increase forever, or do we approach a value? Do we decrease forever? That sort of thing. Once we figured out all of that stuff, then we can start graphing. We will break up the graph by critical points and points of inflection and vertical asymptotes. Then we can see where f is increasing in each interval and where f is decreasing in each interval. We'll figure out where the function is at each point of interest, meaning where are the critical points, where are the points of inflection. And then we'll connect them using proper concavity and whether or not we're increasing, decreasing. We'll sketch the asymptotes where needed as well. To say this step-by-step process in a shorter way, we're going to find the critical points, points of inflection, vertical asymptotes, and then see what happens in each of the sub-intervals between those points. Let's do example 1. We want to sketch the curve using the first and second derivatives. My function here is x to the third minus 2x squared minus 6x minus 3. This is a polynomial, so the domain is all real numbers. There's going to be no asymptotes because we're never dividing by 0. Then I go and take the first derivative. The first derivative is 3x squared minus 4x minus 6. The second derivative is going to be 6x minus 4. So we have my first and second derivative. Let's look for critical points. Critical points happen when the first derivative is 0. 3x squared minus 4x minus 6. Let's see if this one factors. This one does not factor, it appears. 3 times negative 6 is negative 18. Factors of negative 18, there's no factors of negative 18 that add up to 4. So I don't think this one factors. So I'm going to have to use the quadratic formula, opposite of b plus or minus the square root of b squared minus 4 times a times c all divided by 2a. So I got two critical values. One of them is when I use a plus, the other is when I use a minus. That square root, negative 4 squared minus 4 times 3 times negative 6 becomes 88. So really, these two critical values, one is 4 plus the square root of 88 divided by 6. The other is 4 minus the square root of 88 divided by 6. If you want to, you can see those a little bit. You can use rounded numbers if you'd like. When I did 4 plus square root of 88 over 6, that was approximately 2.23. I'm going to put equal to 2.23, even though that's rounded. And when you do the subtraction one, I get negative 0.90 when I round to 2 decimal places. All right. So those are the critical values. The critical points I would get by plugging those numbers into my original function. So my critical points One of them I know has x value approximately 2.23. So I'd plug in 2.23 into my original function, take 2.23 cubed minus 2 times 2.23 squared minus 6 times 2.23 minus 3. And again, output is approximately negative 15.24. Again, I'm rounding that to a couple of decimal places. So that's the first critical point. The second critical point is obviously negative 0.9. You can also plug that in to the original equation. Again, original equation is x cubed, so you got to plug in negative 0.9 cubed minus 2 times negative 0.9 squared minus 6 times negative 0.9 minus 3. And I got a 0.05 when I rounded 2 decimal places. So when I did that, I got those being my 2 critical points. Those are different than the points of inflection. Remember, the points of inflection happen when the second derivative is equal to 0. In this case, my second derivative, if you recall, was up here, 6x minus 4. So 6x minus 4. Solving for x would yield x is equal to 2/3 or 0.67 when I round to 2 decimal places. Now that's the x value for the point of inflection. The actual point of inflection would be what you get when you plug in 0.67 into the original function f of x. Let me go ahead and do that. I haven't done that yet. 0.67 cubed minus 2 times 0.67 squared minus 6 times 0.67 minus 3. If I were more careful, I'd use the fraction version of 2/3 instead of 0.67. But for right now, I'm just going to plug in the decimal version. So the rounded version would be about 0.67 to about negative 7.62. So now we have the critical points and we have the point of inflection. We know that the domain is all real numbers. We know that there are no vertical asymptotes because this is a polynomial function. The last thing that we want to find before I turn to my graph paper is the behavior of f of x as x travels towards infinity or negative infinity. So what's going to happen to the limit as x goes to infinity of my function x, f of x, excuse me. As my function f of x goes to infinity, you're going to get really big numbers cubed. That term is going to dominate. And if you take a really big number and cube it, it's going to still be a really big number. And in particular, if it's a positive number and you cube it, it's going to be still really big number, which is positive. So the limit as f of x, of f of x as x goes to infinity is infinity. If I switch that positive infinity to a negative infinity, well, plugging in negative really big numbers and cubing them also gives negative really big numbers. So as x travels towards negative infinity, the y value travels towards negative infinity as well. Once I have all of these points, I can go ahead and start graphing. I'm going to graph this on Desmos. Instead of plugging in the function, I'm going to do this the old-fashioned way. Take the points that I just found, the critical point of 2.23, comma, negative 15.29, I believe. Oh, I'm sorry, negative 15.24. That's one of my critical points. My other critical point is negative 0.9, comma, 0.05. My point of inflection is 0.67, comma, negative 7.62. I hope that you see what's going on here. We have 3 points. Let me change the points that are critical points to red. We have 2 critical points in red, and we have 1 point of inflection that's in green. Also, I know that the limit as x goes to negative infinity is negative infinity. If we're going to draw this, that means to the left of this red critical point, I need to be doing something like this. So we're going to do something like this. We're going to go to that point up there. Because the limit as x goes to positive infinity, you get infinity. Your graph is going to be doing something like that on the right. This point of inflection is a point where the second derivative could change, so the concavity could change. If you further break this up into concavity, you could find out that at this critical point of negative 0.9, comma, 0.05, we are concave down. So we're concave down there. I can show you how that works. So concave down, we're parabolic shape pointing down. And at this other critical point of 2.23, negative 15.24, we're concave up. So if I were to curve sketch this, I'd be getting some shape that looks like this. I didn't draw it quite as smooth as I would have liked, but I think you can make out the general pattern. We're concave down anywhere to the left of this inflection point at 0.67, comma, negative 0.762, and then we're concave up beyond there. If you want, you can algebraically calculate that as well, the concavity, I mean. If I want to figure out the concavity, well, the point of inflection is the only place where we could change it. So to the left of that point, I just need to pick an x value of something less than 0.67. I'm going to pick 0. And remember, I need to plug that into the second derivative. The second derivative was 6x minus 4. So 6 times 0 minus 4 gives me a negative 4. That means the concavity to the left of 0.67 is concave down, just like I said. And we can do that onto the right as well. So to the right of that point, well, pick a number that's bigger than 0.67. Pick an x value of, let's say, 1. Plug 1 into the second derivative. 6 times 1 minus 4 is 2, which is positive. That means that to the right of this point, my graph is concave up. So the point of inflection tells me concavity. Points that are critical points tell me where they could turn. This one is sort of forced on me through basic common sense, but you can do it other ways as well. So once again, I know that we're concave down to the left of this point. Oops. So we know it's going to be turned concave down. We're going off to negative infinity as we move to the left. To the right of the point of inflection, it's concave up. The only place where we can change direction is at the critical points. So it's somewhere, the graph looks something like this. By all means, because we have calculators which can graph functions and computers which can graph functions, we should probably check our answer each time we do this, just so that we can understand that we got the graph right. I'm going to type that into Desmos, either f of x or y equals x to the third minus 2x squared minus 6x minus 3. Yeah, I drew it a little bit more elongated, but you can see that the general pattern, the general shape, is what we thought it was. So the general shape is exactly what we thought it was, although I had drawn it a little bit thicker. So there you go. That's how that works. What I would like you to do is to sketch the curve using the first and second derivatives. You can check that you're getting the general shape right by checking it on your calculator or on a computer program. But I want you to do that for this curve here. So for this equation, sketch the curve just like we did in the previous example. I'll finish this up in the next video.